Okay, I think we will get started. First, welcome back from Thanksgiving. It's good to see everybody back in fall break. I hope everyone had a little bit of time to start to rest after a big semester. So, it is my pleasure to welcome today Dr. Shkolnik from Arizona State University. She is a professor of astrophysics in the School of Earth and Space Exploration, and she's an associate director for the Interplanetary Initiative. She's an expert on stars, planets, exoplanets, and all of their interactions, and certainly our sun as well. She is the PI of the NASA Sparks mission. That's the Star Planet Activity Research CubeSat, and she's also the PI of UV Scope. That is the ultraviolet spectroscopic characterization of planets and their environments, which is a mid-X mission. She also leads several major campaigns with HST. She's a member of the Astro 2020 Decadal, and you should definitely make sure you get a chance to ask her afterwards about her work with the Habitable Worlds Observatory. So with that, please welcome our guest.
On. There we go. All right. It's all working now. Thank you so much for the introduction. Thank you for the invitation. I've had a wonderful day. I mean, really wonderful. So many great people to talk to. And my brain is filled with things to follow up on and papers to read afterwards, and also shamed into my ignorance of the solar system space weather, so which I am here to learn more about from all of you, but also to teach you a little bit about what we don't know about exospace weather. Okay, so the title of my talk is Environment Matters: How Stellar Emissions Impact Atmospheres of Exoplanets. Now, emissions here is plural, which we don't usually use, but the reason why is because I'm going to talk about high energy photons and also particles. So exospace weather is generally pretty new. We've been thinking about it for a while, but we have very little data. And so when you have no data, it's really hard to spend a lot of time thinking about it and talking about it. So it's not like we in the exoplanet and stellar world have been neglectful of it. We know it's important. We just haven't had much to work with. But I think now it's really time to get serious about it, because we need to understand what's happening to all the atmospheres that we're looking for and can't find. And especially with the Habitable Worlds Observatory now really in earnest getting started, when we're actually going to be building an entire space telescope where one of its main driving science cases is the search for life. We better get our act together before then. So we have a couple decades, but we got to get started. Okay, and this here just is a list of the people who contributed to much of the work that I am presenting. These are my current or former postdocs, some of whom have gone on to become their own grown-up astronomers. And so also the Sparks team, this is, as you mentioned, this is a CubeSat. We have lots of people, so I'm going to list them on a different slide. So they're coming up too. Okay, here's a beautiful picture that I found on the internet, one of the recent ones, at least new to me, of trying to represent the diversity of exoplanets. Now there's many thousands, like over 5,000 exoplanets now known. And I was going to print this off and post it on my wall. And then it made me kind of sad, because I realized that this diversity of exoplanets is in fact just different colors of planets in our solar system, which made me feel like we don't even have the imagination that we need in order to understand the wide variety of exoplanets. So I don't have the slide here, but you guys can imagine, you've probably seen it, the mass radius plot of all 5,000 exoplanets that have been detected, at least transiting ones. And our solar system is just a tiny line on those, right? Like there's way more to understand there. And the reason then is to think about, well, our solar system, let's look at the terrestrial planets. We had a nice conversation today about the differences between Venus, Mars, and Earth, and they all formed in the same disk around the same star. Now imagine our entire population here, right, of exoplanets where they formed in different disks for the most part. and around different kinds of stars. And so we really have to keep in mind, and perhaps it's preaching to the converted in some of you here, but it never hurts to remind you that entire systems, not individual planets, shape the conditions for planet formation, evolution, and habitability. Okay? And like I said, we are interested, many of us, and maybe many of you in the room are interested in exoplanet habitability and habitability in our own solar system. And so we have to think about what are the stellar and planetary properties that create habitable conditions. And it's really a hot mess, and I'm sure we all can appreciate that. And so I'm not going to talk about the planet properties today. I'm going to talk specifically about the stars' properties. And hopefully we can, we've been talking a lot about bringing groups together, the interdisciplinary nature of many efforts going on right now of bringing planetary science people and stellar people together and heliophysics people together in order to talk about this. But I'm going to today talk just about the star and pretty much the impact that it has on its planets. All right, so since we have, I think, a diverse group, I'm going to go through a little bit of stellar jargon here to make sure we're all on the same page. So different types of stars provide opportunities and challenges for planet characterization. And what you might have heard lots of emphasis on M stars. And the reason why, there are a few reasons why we focus on these M stars. One is because they're smaller than the sun. It's easier to detect transiting planets and radial velocity planets around them. But it's not just a matter of looking for the keys under the lamppost, if you know that expression, right? We also, even though it's easier to find those planets and easier to find habitable zone planets, it's also where most habitable zone planets exist in our galaxy. M dwarfs make up 75% of all the stars in our galaxy and are the dominant hosts of all rocky planets, including those in the habitable zone. And if you work out the statistics that we have learned from Kepler and TESS, it turns out that there's roughly 40 to 50 billion rocky planets around low-mass stars in the habitable zone in our one galaxy. So if you really care about the distribution of habitable environments in our galaxy, as I do, you're going to have to care about the M stars, which come with their own challenges, which you'll hear about because they're very active, they flare more, and potentially their planets might lose their atmospheres. But of course, we also care about the sun because we know we have an example of one where life actually evolved around a sun-like star, and that is us, right? So just to go back to the basics, just so we understand it here I'm plotting mass and luminosity for a bunch of stars. And one thing you may hear a lot is M dwarfs this and M dwarfs that, but really M dwarfs span 3 orders of magnitude in luminosity. So throughout this talk, I'm going to be distinguishing between early M stars, which are these more massive ones, and late M stars, like the famous TRAPPIST system, which is at about 0.1 solar masses. So early M stars and late M stars they're just called M stars, but they are completely different from one another, and it's just a poor nomenclature. Where am I? Oh, here we go. Okay, thank you. Okay, so you might have also then, because of the M stars being easier to detect planets around, you could have heard this expression, the M dwarf opportunity. We talk about this a lot in the field. But the more we focus on M stars, the harder it is to convince ourselves that atmospheres might actually exist on those planets. And so we are also focusing on what I call, I don't think this has made it into common jargon yet, the sun-like star imperative. And it is an imperative because if we're going to look for life, at least we've got to start somewhere. And we know that life can evolve around a sun-like star. So let's start there. And that is, in fact, where the Habitable Worlds Observatory is going to be focusing its energy on, is on sun-like stars, not M stars, for a variety of technical reasons. That's what it's going to be doing. And then there's the potential K-dwarf sweet spot. We've also called it the K-dwarf advantage. That is these kind of intermediate stars up here, where maybe they're the ones that are less active than M stars. Their habitable zones are further out, but it could still be kind of detectable from the transit method. So maybe that's the case. So I'm going to talk about all of this in some capacity. So here's the outline of my talk. First, I'll tell you about why it matters, why the environment matters. Then I'll talk about photons, and then I'll talk about particles. Now, I can, if you want, pause between each of these and take some questions, or I can wait to the very end. So if you have a burning question, please just raise your hand. I have no need to get through all my slides. It's okay. I don't mind skipping slides to engage with you guys, because that's what we're here for. All right, so are there any questions? I guess I'll pause. Are there any questions from anything I've said thus far? No. Thank you. Okay. All right. So here is a diagram that my son made for me when he was 13, and I use it all the time because it's really helpful to just kind of have a schematic and look at the impact that the radiation from the star has on different layers of a planet's atmosphere. In this case, it's just a generic planet, but you can imagine that this is a terrestrial planet. So you have the near UV, the far UV, the EUV, which is extreme UV, and the X-ray are all photons that are absorbed at different atmospheric levels, and the particles as well. And if you look at the exosphere, right, if you look at that's the outermost region, you might want to know how exactly is the planet impacted by the high energy radiation, especially the XUV. XUV is what we call X-ray and EUV smushed together. And there is, like, these are the wavelengths that are impacting atmospheric loss. And then the far UV kind of penetrates a bit further, and we can ask questions about the upper atmosphere. What roles do the upper atmospheric properties play in the escape process? Because this is also where you get the lifting into the exosphere. Also, this is where you can get hazes and clouds forming, and so that's also something that we care about, especially for transmission spectroscopy. And in the lower atmosphere, when the longer, but still UV wavelengths penetrate, they can impact your planetary atmosphere photochemically, such that you actually change the chemistry of the planet independent of whether or not life exists on the planet or not. And so when you're interpreting a particular spectrum, you want to understand what is the context within which you are observing the spectrum. So we spend a lot of time, and there are people in this room, Sebastian, David, who spend a lot of time looking and thinking about the high energy spectrum of planet-host stars. Our group has been doing similar things, and we're trying to find ways to predict these high energy wavelengths that are not currently observable. And in some cases will never be observable because the stars are too far away. And so we have spent a lot of time, this is work done by Sarah Peacock when she was a graduate student at University of Arizona, but also on our team, where she took the old photospheric models, these are the old Phoenix models you might have heard about, where they calculate the photospheric spectrum of a low mass star. And it's this red curve here, right? And it's not that they were wrong, even though they wildly, by many orders of magnitude, underpredict the high energy radiation of an M star. But they were just never designed to, because people didn't know that they had to care about it. And so in the early days, like, early meaning like even 10 years ago, people were using these red models and applying them to exoplanet atmospheres and calculating photochemical impacts. When they were, as you can see, if you draw your eye down, you would be 6, 7, 8 magnitudes off. Right? And so now we've had a big push. The community has definitely been pushing into understanding these high energy radiation environments, and it's relatively been successful thanks to HST, which has been our main workhorse for UV spectroscopy. So I'm just going to run through what I think, and others here might have additional questions to add, what I think are the 4 big questions in exoplanets research today that are governed, or we believe they are governed, primarily by stellar high energy radiation. So it's just a quick run through. One is this result that came from Kepler that shows that small planets come in 2 sizes, right? Have you guys heard about this, where you have this bimodal distribution in planetary radii? And is it because of impact of stellar radiation and actually sculpting of planetary atmospheres such that you can only get that some lose their atmospheres efficiently and some don't? Probably that is because of the high impact radiation or high energy radiation impacting these planets. That is not confirmed yet. That is a likely scenario. We also have observations of cometary like tails, where you see active escape from planets during transits in the ultraviolet. And here's a very nice movie from John McCann, a former graduate student of Ruth Marie Clay's, where they've modeled for different stellar winds, right? Here you have a weak wind, an intermediate wind, and a strong wind, and you end up with a different kind of cometary tail that you can observe. And what I particularly love about this kind of work is this is a case where you can use the planet as a probe of the stellar wind, which I love, right? And so, as you'll hear soon, we have a very hard time measuring the wind off the star, and this is one way that we might be able to do it. The next big question is, as I already alluded to, is that we have JWST spectra of small planets that are coming out pretty flat, right? Or at least there could be a thin atmosphere, but we're ruling out some atmospheres. Here's just one example. This is of a rocky planet around LHS 475b, and you can see the data here in white. And it's ruling out a methane atmosphere. It's ruling out maybe there's a carbon dioxide model there, but the yellow line here is a flat, and it's completely consistent. So the question is, does this planet have an atmosphere around this M star? It certainly doesn't have a thick one, and if so, why not? And the last of these comes back to habitability again, is how will we detect biosignatures? Here's an example from the Virtual Planet Laboratory, Vicki Meadows' outfit up in Washington, where they are modeling the reflectivity of an Earth planet around a sun-like star. So this is what we're going to be doing with Habitable Worlds Observatory under different conditions. So here this is exactly an Earth atmosphere, but looking at a star that's an M star like GJ876, but through time. So when it's younger, as it gets older, and so on. And what you see is that the spectrum is noticeably different. And worst of all, this ozone feature, which we are touting as an excellent biosignature, is completely dependent on the UV environment. So you could have life on this planet, right? And some of these might be destroyed. So you might be looking for water and methane, and it's actually destroyed through the photochemistry. Or you could have no life on this planet, and you have a false positive. So what's amazing about these M stars is you can have both an opportunity for a false positive and a false negative with the same issue. So like we got to get our stuff together. Okay, being recorded, no cursing. Okay, okay. So any questions on that? Does anyone have any other questions in exoplanet science that you want to add to my list of 4? Because I just threw in 4, but yeah.
The microphone, sorry. So if you do want to ask a question, please use the mic. But so did you look at other stars? And well, I'll start with that. Did you look at other stars?
This particular effort has just been looking on M stars.
Okay.
So far, it's just M stars.
Okay.
I don't think they have looked yet on sun-like stars.
Okay. And then, to some degree, while there's like this age, on the one hand, it's like, oh my gosh, but then our sun, I mean, that's in some ways like, this is sort of a good thing because, right, like early systems, you wouldn't necessarily, based of course on us, you wouldn't necessarily expect to see life or biosignatures. So wouldn't that change then the target age? This seems like a good, like, if anything, I mean, on the one hand, I see your point, like, oh no, you don't see things, but then wouldn't this help guide maybe the stellar age? Or is that the sort of
no? I think you're totally right. Like we can use this information with enough parameter space covered by these models. We can then say, okay, we're not going to be sensitive to life from this age to this age. Let's look at something older or younger or whatever the case may be, depending on what you're looking for and its distance. You have to, also keep the distance of the planet. And the habitable zone distance, of course, shifts with the mass of the star. Right? If a star is smaller and cooler, the habitable zone comes in very close, which is in itself could be problematic because, let's say, for Proxima Centauri, I'll just give an example. Proxima Centauri is our nearest stellar neighbor. It's also our nearest exoplanet, Proxima b, and will forever be our nearest exoplanet. And it is in the habitable zone at only 10 stellar radii. So 10 stellar radii is the Alphane radius, roughly, of the sun, right? And it changes, and it's not totally spherical and all that stuff. I was talking with someone about that today. But yes, we have to, you'll see on my very last slide, essentially begs for more models and more modeling. We really have not probed the parameter space. We have not done the same exercise on other biosignatures as has been done on oxygen. Oxygen has really been put through the ringer, but it hasn't been done yet on all of them.
Okay, thank you. Any others? Oh, hang on. No, it's okay. I need to get more steps.
So just staring at this plot, I'm super curious about the I guess your thoughts of how well we know what the spectrum of the star would look like at these different ages. But then also kind of looking forward to these observations, that ozone feature there, to really interpret it, do we need to know the UV spectrum of the star right now, last week, last month, last year, last millennia? What are the timescales that you think are most important for this?
There is a paper, Tilly et al. 2019, if you know it, where they just bombard one planet with one giant flare, and it takes 50 years for the atmosphere to recover, right, where the ozone column density is destroyed from one flare. Now, that's pretty much telling you that we have lots more work to do, lots of modeling. I'll show you some new models where we have a full flare frequency distribution of using accurate data. But we have not yet modeled firm timescales for any of this because we're still collecting the actual data. We're still actually collecting how different is a UV spectrum of this M3 compared to that M3, right? There are differences. There could be differences based on rotational modulation. There's differences based on stellar activity cycles. A very nice paper just came out with an activity cycle on Proxima Centauri, if you're curious on that. And of course, flaring and general variability. So it's hard to know. It's hard to know. That's why we're trying to do things in an evolutionary way, right? Let's just see what the whole thing's exposed to. If the atmosphere can survive the first 100 million years, great. If it cannot, now we start talking about secondary atmospheres, tertiary atmospheres. What does that really mean? Those kinds of things. So there's a huge parameter space we are just now starting to chip away at, because I'll be honest, it took a long time, and you'll remember this, Zach, to convince exoplanet people to even say what the spectral type of their host star was in talks, right? Like, it just did not matter. And now I think we're changing that. I think this has become more appreciated.
There will be questions after. So,
yeah.
Just kidding though. We have one more.
Sorry, one quick one. I'm just curious, for the virtual planetary laboratory and the new UV observations, were those Hubble observations? Were those time domain? I'm just curious about those.
Oh, those new UV. Oh, those ones. Those ones were Hubble UV spectra. Yeah. So what we did was we used Hubble UV spectroscopy in far UV, and then Sarah Peacock is able to predict. She uses those to calculate the full spectrum. But really, for the photochemistry, it's really near UV and far UV. Actually, the EUV doesn't penetrate down to these heights in the planet atmosphere. So for photochemistry, you care more about far UV and near UV and less about XUV. OK, let's talk about the photons then. OK. I'm going to try and speed up this a little bit because I do like the questions, and it's more interesting to me also. So we have this large program called HAZMAT, the Habitable Zones and M-star Activity Across Time. My graduate student, Tyler Ritchie-Yowell, she went then and did the HAZCAT program, Habitable Zones and K-star Activity Across Time, and she now has her own student doing the flare frequency distributions of K-stars. And now with Habitable Worlds Observatory, the HAZGAT program is going to get cracking soon now that people care about sun-like stars again. So that's all excellent. We used X-ray data from ROSAT, GALAX data, and HST data, but let's just get to the results. So here's kind of the summary plot from one of Tyler's papers. Is essentially comparing, here's what I'm looking at, far UV flux at the habitable zone, so this is now scaled to the habitable zone of the star, as a function of age, and this is how things evolve. Late M's have much more flux in the far UV in the habitable zone as compared to early M's and K stars. What's interesting is that the K stars are actually right up with the early M stars. They're not that different. We thought that the K stars would be down here closer to sun-like stars, but they turn out that even in the habitable zone, they are comparable to early M's. So maybe that might lead us to think that that K-star advantage, as we used to call it, or the K-star sweet spot might not be an advantage or a sweet spot. And I refer you to Tyler Ritchie-Owell's papers on, she did some great work on K-star stalling, that the actual rotational evolution of K-stars is different than what you expect for sun-like stars and for M stars. And so K-stars, weirdly enough, are kind of special. And that was a really exciting result. But I'm not going to talk too much about that, but that explains why they're more active than you think they should be. Another thing that with all these UV observatories online, some not anymore, of course, GALEX is no longer functioning, but it left us with a beautiful archive. Here's just an example of one M-star flare observed by GALEX. It's a super flare that increased by 10 UV magnitudes. That's a factor of 9,000 in the near UV. I think this is the near UV. And so it's just, I mean, these kinds of things are bonkers. I don't know. We also found this HAZ flare in HST data. This is a young M-star, it's 40 million years old. Paper led by Park Lloyd. Some of you might know him. He did his PhD here with Kevin. And so you can see that we detected in the far UV an increase of a factor of almost 200 in just 200 seconds. So much so, I don't know if you guys know this, but HST has kind of banned us now from looking at nearby active M stars because they're afraid that we're going to damage their detectors. Yes, I think you feel my pain. And once we saw this, they're like, that's enough for you, and they made us change a whole bunch of targets. So, so we actually cannot detect, we cannot observe anymore with our one single UV spectrograph available to us active nearby M stars to get the data that we want. And so that's unfortunate. Here's a program that Ward was part of, right? Ward, you were part of this, and you guys also remember Meredith McGregor. We did this program where we did a bunch of simultaneous observations of Proxima Centauri. We had 36 hours of HST time on it, which was the longest HST had ever spent on a single star. And we saw this flare that in the FUV continuum increased by a factor of 14,000. And the same flare was detected in TESS, and it was only a factor of 10. So you see, so just imagine, like we have all these beautiful flares from TESS, and they're all going up by factors of 20%, 40%, factors of 2, factors of 10. And it could be factors of 14,000 in the far UV. I mean, what are we really learning? So we just got to make those connections. I know that people here are working really hard on it. This is an amazing department. You guys are really tackling this from so many angles. And so one of the main results of the HAZMAT program was to look at the, this also includes the your local muscles group data as well. Of course, both led by Park Lloyd, because of course we snatched him up at ASU once he was free to go. And but what you can see is that this is what we call a flare frequency distribution. So you have the frequency of the flares per day, and here's just total energy in the far ultraviolet. And here's the HAZ flare, that big one that we detected, that happens once per day on a young M-star, right? This is a super flare by any stretch of the imagination. And so essentially, super flares happen every day. And so if you are a planet 10 stellar radii away, this is your life. So let's see. So possible loss of primordial atmosphere. So this is new work actually done by Laura Amaral, recent graduate from Mexico. She worked with Antigua Segura, and I hired her. And she is one of very few people, maybe one of two people, who is trying to model atmospheric escape using realistic flare frequency distributions in the ultraviolet. And the point of this plot is here you're seeing two super Earths. You have a super Earth at 2 Earth masses, which is the solid line. And if you include quiescence only, you might have an atmosphere after 10 billion years. If you include flaring, you might not have an atmosphere after 10 billion years. And that's the point of it. Uh-oh, why does my computer want to shut down? Hold on. Cancel. Something I touched here, why did my computer shut down? Okay, so I'm not going to go through all these plots. You guys have to see her paper. She just submitted a paper where she did this similar analysis of using flares, comparing the importance of needing flares versus not needing flares for the AU mix system, which is very young. And because it's young, it's also very elevated in the quiescent UV. And so what you can tell here, I know this plot is too complicated to go through, but the bottom line is if you take the AU mix D, which is very close by, it actually does not even need the flares to destroy its primordial atmosphere because the quiescence is so high at that age and the distance so close. Now, if you were in the habitable zone, if you took AU mix D and put it in the habitable zone, then you're kind of in this spot where they're equally contributors. And then if you go further out and you put it out past the habitable zone, you might retain your atmosphere. So this is a parameter space we're starting to explore. So one of the challenges, though, is you don't really know. We've only observed down to the Has flare in the UV, right? So we need to really understand what's happening in this range. Does the flare frequency distribution curve? You can't have an infinite energy, right, flare. At some point, this will turn over. And we want to see these rare flares. Remember, HST observed, the longest it observed any M star was for 36 hours. So what if you can observe for a month on a single star? And that is the point of SPARCS. So SPARCS is a Star Planet Activity Research CubeSat. The whole goal is to have dual band photometry, the near UV and the far UV, simultaneously observing low mass stars. And we have a science program that I just mentioned where we're going to spend roughly a month, between 2 weeks and a month per target to catch the rarest and strongest flares. We have a technology demonstration program, which is also part of the APRA. It's funded by the NASA APRA program. I know lots of you have participated in that. And so our technology program is to demonstrate some important UV technologies that could potentially be used for Habitable Worlds Observatory, but has already increased itself just in the development of it, TRL, so that's going to be used in UVEX, which is the next already selected NASA UV mission. And then, of course, all of these APRAs do a great job in training mission leaders, not just PIs, because anyone in missions here know that we have lots of leaders, and everyone should be a leader in whatever capacity they can on a mission. This is our mission team. Lots of names to go through. The green names are the junior folks. There's a couple TBDs here. I just wanted to point out that when we do launch, we don't have our science students and postdocs yet hired. So if anyone here, keep an eye out next year for some job postings. This is our, I'm going to just skip this, but essentially we want to fly the high QE delta dope detectors. For those of you who are in the UV world know what I'm talking about. And we're also testing the integrated filters, and these are very important for red rejection of your observation, because M stars are very red, right? So you're literally getting 1 million more red photons than you are UV photons, so you have to be very good at rejecting your red photons. Our design is very simple. We have a small 9-centimeter telescope, we have a dichroic, and it feeds an NUV detector and reflects off to the far UV detector. And again, we want to just stare and stare and stare. Now, we're going to stare at a whole field. Our field is going to be 40 arc minutes across, so we do have lots of other targets. We can only downlink 10 postage stamps per field, but we will be opening that up for recommendations and proposals for people who want to take our fields and find other objects in there that they might want this kind of observations, a month long of observations. We will also, once we publish our target list all in this full schedule, I think people who do multi-wavelength observations of flares might be interested in doing some ground-based observing. So we're going to do that. And where is SPARCS today? Well, SPARCS is in our lab. We have a very well-designed clean room for UV detectors where it needs specialized processes for contamination control. We're getting ready for TVAC testing. And so it's all kind of like all wrapped up. So cute in the lab. And where is it going? Well, the spacecraft will be done by the end of this month, actually. So assuming everything goes well with the TVAC testing, of course. So we're very excited. But our launch, which was supposed to be in February, the primary mission was delayed until Q4 2025. So we actually have to put it into storage for a while. And so that's a bummer. But it's better that we wait on them because they ain't waiting for us. So that's okay. So our plan is to go to a sun-synchronous orbit at the end of next year. So stay tuned for that. All right. I'm going to not take questions right now because I want to get through some of the other stuff. Okay, so now we're going to move on to particles. So I think we're getting a handle on the photon, right? We know what we need. We're working our butts off to get it. Now, what about the particles? So work that has been done here with Jeff. Jeff's here, right? So we have the astrospheres. Actually, I remember when I was here in 2015, you gave me a private tutorial about astrospheres, and it was awesome. And you taught me how you guys do it. And it's amazing, and it gives you some sense of the solar or stellar wind as observed through the Lyman alpha profile. And so what you can see, I assume you all kind of maybe know this here, but you can observe the Lyman alpha profile, which is quite complex. There's lots of stuff going on there, but there's additional absorption that happens in this hydrogen wall as the heliosphere, or in this case, the astrosphere, plows through the ISM. Another way that this astrosphere has just recently been detected, I think this was for the first time in this paper in 2024, where they observed the stellar wind charge exchange through, what do they call it, actually spatially resolved X-ray observations. So I found this to be a very interesting paper. For the sake of planets close into their host stars, I am more interested right now in coronal mass ejections. Now, these are huge expulsions of plasma from the sun, roughly 10 to the 15 grams, primarily of protons and electrons at huge speeds. And this happens on the sun all the time, right? Especially now that we're close to solar max, we're probably at around 5 per day. Now, they're not all hitting the Earth. Only about 1% to 2% actually hit the Earth. But if you're going at 5 per day, that's a lot per year. And the CMEs, I think, are quite, there are no CMEs right now, confirmed CMEs detected in stars other than our sun. Does anyone know of any? Does they want to challenge that statement? Yeah. Yes. Yes.
There are observations of decreases in X-ray emission from stars that are interpreted as due to coronal mass ejections.
Right. The coronal dimming. I'll show you an example of that.
So, yeah.
Yep, 100%. So there are several candidates out there. We have not yet confirmed them, and then to have a conversation. It's worth a conversation some other time. What does it mean to confirm a coronal mass ejection on another star? But at the moment, these are all candidates by my interpretation, and I think the community is broadly speaking. This is just for fun because this is a Parker Solar Probe movie, and which really should be sonified. The sonification of this movie is a must. I don't know whom to tell, but I'm going to tell you. Please send this to someone, because look, this is the Parker Solar Probe getting closer and closer to the sun in a 10-day period. And it hits 5 CMEs, just whack it. And anyway, that's just a fun movie every time we talk about CMEs. But I think that if you are coming close, as our close-in planets that we are studying and observing right now are coming this close to their stars, or they exist this close to their stars, they have a completely different environment that they're exposed to than we are here in our very comfortable 1 astronomical unit. So let's learn from the sun of how to detect CMEs. And here I give some references to what you just mentioned, Jeff, about coronal dimming in the X-ray and in the UV. Again, there's candidates, there's Doppler shifting and Doppler broadening of lines. If you actually have coronal spectroscopic lines, as the material moves, you could have it be Doppler shifted or Doppler broadened. And type 2 radio bursts. In all these cases, exist some candidates, but no confirmations. okay? But we should be learning from the sun, and that's kind of where I'm going with this, is how are we going to be leveraging what we know about the sun and studying other systems. So one amazing thing I learned, in the last year, is that while flares and CMEs can happen together, a CME does not cause a flare, and a flare does not cause a CME, which I find completely fascinating. But they're the result of the same phenomenon, the same physical phenomenon, namely magnetic reconnection events. But the fact that they are associated means we should still be able to see them. And the reason why I went down this path is because flares, as I showed you before, are routinely observed in other stars, while CMEs are not. So can we use flares to say anything about CMEs? And so what we're doing is we're taking SDO data, we're pulling out a bunch of flares. Here is just a far UV image from SDO, 1 month of the sun. You can see all the beautiful flares. And we are trying to map them to CMEs that are observed by LASCO, which is aboard SOHO. Now, this has been done before in X-ray, and this is our analysis of X-ray expanding into 2 solar cycles. Previous work had less data, but we get essentially the same results. Here I'm plotting the X-ray flare peak flux with CME mass as reported by LASCO. And if you take away the blue line, it's just a big cloud of I don't know what. But you can bin them and you can get a significant correlation, but it is tough. I mean, this is telling us, either this is going to be much, much harder than we thought to use the sun in order to do this for other stars, or that given the lack of all of the data, we got to start somewhere, and this is not zero information. This is still some information, at least for potentially solar-type stars. My graduate student, Mary Park, who's been doing this work, just submitted a paper that also included the real analysis of all the X-ray data, but also the far UV, because we are getting many more far UV observatories coming online, including Ultrasat, and SPARCS, and UVEX, and so on. And so let's see if we can do this in the far UV. And similarly, you get a pretty giant cloud, but some significant correlation in there anyway. So in absence of all other data, this is where we're going to start. So what about our beloved M stars? Because right now one can say, okay, we can apply these correlations really just to sun-like stars, right? You can't really, in good faith, apply this to M stars. Yeah. Oh, sure.
It's the peak flux of the disk or the particular location, and at what time. Is it earlier? Because the particles will take some time to arrive, so I'm not sure I quite understand this plot.
Right. So we have a matching mechanism that is both spatially and temporally we have aligned. So we have to make sure that I think it's 80 minutes, because you're right, the particles hit at a different time. So we have I think it's within 80 minutes, so you have a flare, but also you have the spatial, because we have disk resolved, so we know where the flare is coming from. And so we have maybe plus or minus 30 degrees in space. Yeah. It's hard to trace back that exact, it is hard, and that's one of the reasons why I think this is a big scatter plot. And from reading how people measure this, you can also see why it's a scatter plot, because the uncertainties on these points should be 30 to 50%, I would say, in the mass. Okay. What about M stars? What are we going to do? Okay, I don't have any answers either. There are a couple papers, though, that are thinking about this a bit, and there's one paper and one hopefully in prep. So Julian Alvarado Gomez does have a paper where he talks about magnetic confinement, where you could have a very strong flare, and with a very strong magnetic field, you're actually confining the particles, and therefore your CME does not become a CME. So you could have giant flares, but no CME. That's very interesting. And Moira Jardine presented in New Zealand earlier this year. Another theory, if I remember correctly, it's not a paper yet, so I have to remember from her talk, but the idea that because M stars have lower helicity, because their convection zones are much deeper, their magnetic fields don't get twisted up as much, and you don't get as much reconnection, and so you could have flares without CMEs. So in both these cases, from a completely different perspective, they predict that M stars might have lots of flares, but many fewer CMEs. But again, we have no clue. So in order to try to tackle this, we put together a team of people to do a study run by the Keck Institute for Space Studies. I think some of you have heard of it. Some of you were there with us. There's a great representation from CU Boulder. There's Shannon. There's Dave. You guys remember Erica? She was here, right? And Park. And there could be others who passed through here. Do you guys know Maurice Wilson? He's here now in town at the NSO. There could be others who at some point in their past passed through here, but we got together and we tried to come up with new ways to measure space weather, exospace weather for exosolar planetary systems. And we're coming out with a report this spring where there's going to be a series of findings and recommendations to the broader community so that we can all come together and work this problem out. Here's a few of the recommendations. We don't know what the final recommendations are, but this is like some of the hot topics that we talked about during our workshops is to have dedicated monitoring to collect X-ray and far UV flares of sun-like stars. And then if we can do this also with spectroscopy, we might get also the Doppler shifting. In my opinion, a confirmed CME detection would have both these things observed simultaneously from the same event. Okay? And thank you, Ward, for that approval. We would like more dedicated photon and particle studies of sun as a star. We're doing the best we can. There's so much data, but sun as a star, integrating all the light into a point takes a lot of effort, and you have some sort of biases that come into play there. And then more planet atmospheric modeling. To what accuracy and precision do we need to determine the CME masses? Like right now, as I said, for the sun, the CME mass errors are probably 30 to 50%. Do we need to know the mass of CMEs and the associated density and speeds to have better precision? But for that, we need the models. So, finishing right on time. Thank you, everyone. Here's kind of my final slide. This is how I view the world, which is with flow charts, where we want to understand the high energy radiation environment off the star, right? And there's a bunch of UV missions. It's not just these, there's lots more, hopefully, and we need more. For people who say, we already have a UV mission, we don't need any more, that is incorrect, because each one is doing its own thing, and when you're doing a really great experiment, you really want it to be properly designed for the experiment at hand. And then we need to understand, so we understand the star, we need to understand flares and CMEs, we need to model the heck out of the star, model the planet, understand mass loss, chemistry, climate, all of this in order to understand the observations of the planets themselves. We are going to be looking at planets here also, right? You can do transmission spectroscopy in the UV also, and we have been doing that. But so many more planet characterization studies will actually be coming out from the optical and infrared with bigger missions in the future. But in order to interpret all of these beautiful data that are going to come out, we need to understand all of this. And this really needs more modeling effort. I mean, it's just, it's a real bottleneck, actually, because it's the models that will motivate the new missions, the new observations, and so on. Okay, thank you for your time.
Okay, I will start in this direction and weave this way.
Yeah, great talk. I think this is a topic that is going somewhere. It's going to be really interesting. But I'd like to put you a little bit on the spot by asking a specific question, a yes or no type question. And that is, in the M dwarfs where the planets are extremely close to the star, and even the quiescent radiation is going to bubble off much of the atmosphere, to say nothing of flares, super flares, CMEs, etc. What do you think do you think it's possible or likely that we are ever going to see habitability in M dwarf exoplanets in the habitable zone? Or put differently, does the habitable zone make any sense at all for an M dwarf exoplanet?
Okay, I have to remain agnostic. And I'm not being diplomatic. I am genuinely, I'm being serious. I am genuinely ignorant of all the facts. For instance, Bruce and I, we were having a conversation a couple weeks ago about sequestration in a planet. If the planet, and he taught me, pardon me, if you can tell me if I got wrong, but he taught me that that if you can sequester volatiles into a rocky planet and you lose a primordial atmosphere, you might later on develop a secondary atmosphere. And the models haven't tested it yet. We haven't discussed magnetic fields yet. We really, it's possible that those two papers are correct, that CMEs are not going to be a big factor. So if you wait 1 billion years for the M star to chill out, and then you give it a boost of atmosphere from an internal source, then maybe. I'm not shirking the yes or no question. I'm telling you honestly, I don't know.
Okay, I'm going to up and over some. Okay.
Thank you. You mentioned some models, why M dwarfs might have fewer CMEs. Do we know why on the sun there are flares without CMEs and CMEs without flares? Does that inform those models at all?
I think there is. I think confinement is something that also happens on the sun, where you could have a flare with a filament, so it falls back onto the sun as opposed to being ejected. So that it's not just a model. I mean, that's, I think, genuinely observed. So in that case, you have a flare without a CME. Can you have a CME without a flare? I bet you that you cannot, but the flare could be so weak that we don't observe it. Some excess emission probably comes out, but maybe someone here knows more about this.
I was going to say, here we go.
I can answer that question. Oh, great talk. I was more interested in, I guess, like the importance of the temporal variability or the scale, time scales, the variability in terms of flares. For if you can comment a little bit more on that in terms of like maybe atmospheric loss or if it's even relevant for habitability. And I'm thinking about the flare time series that you showed that has all these little bumps in it. And I'm wondering if that's something that people in this exoplanet community have been looking at in terms of potential diagnostics, or if it's even relevant.
It is relevant. Well, we're figuring out how relevant it is in what cases right now. It's like totally brand new stuff. So Laura Amaral, who just submitted this paper, right, that as I said, like for some of the planets in the EUMIC system, the flares matter, and for some they don't matter. So it depends on the system, depends on the age, depends on the distance, depends on the mass of the planet, right? Because you're going to evaporate a planet faster if it's smaller, right, than a bigger planet. As far as time, so I think we're just now getting going. So maybe in a year or two, we'll have a bit more data and more models to share.
Hi. Thank you for the interesting talk. Yeah. Thank you.
Hi.
Yeah, I have actually a lot of questions, but I will ask a specific. Can you go back to the presentation page on hazmat, and age and UV and REM, late M, KNG?
Yeah, I'm finding it. 1 second.
And I think most of the trend is going down as a function of age, but in the case of
the late M,
it's why going up?
That's a great question. I'll tell you why. Because the late M's take a lot longer to condense onto the main sequence. And as they go from being much bigger with much lower gravity and they get to higher gravity, they spin up. And so as you know, rotation, right? Rotation and activity are correlated. So they go from being slower, less active, down to faster rotators and therefore more active because they just condense later. But good that you noticed.
Maybe important for planet, right?
What's that?
Planetary atmosphere form first generation planetary atmosphere around that age, right?
Or earlier.
Oh yeah.
Yeah.
Mm-hmm.
Great talk.
Thank you.
This is two-part about sparks. The first is I'm curious how you determine which targets to look at. And the second is I'm curious how you protect the sparks instruments against these high energy flares. Especially since Hubble is a little
Hesitant.
hesitant to look at them.
Yeah.
And do you anticipate to see flares that are, stronger than, let's say, monthly flares or rarer?
I hope so, for the last question. Okay, the first question is how do we design our target list? Because I personally, and not everyone feels this way, but I think that the evolution is the whole story. Time is its own context, right? So looking at a star right now does not tell you the whole story. So I'm very interested in the history of a planetary system. So like the HAZMAT program, which looked at stars of different ages, Sparks will do the same. We have young stars, intermediate stars, and old stars. So it's in 3 bins because it's hard to do. And some of them have known planets, like AUMIC, and some don't because we're more interested in the statistical experiment, not necessarily the specific planets. The second question was how are we going to protect? That's a great question. I really appreciate that you asked this because it was a lot of work to sort this out because we had started designing sparks before we detected the HAZ flare, this giant flare, and before HST cut us off from active M stars. So Tahino, I was telling you about, our lead software engineer, he coded up dynamic exposure control for sparks, which would be the first time it flies in space, where as soon as it sees, so it'll have onboard processing, as soon as it sees it go up, it reduces the exposure times immediately so you don't saturate your detector continuously. And you immediately do that in both bands. So thank you for asking.
Hi. So I'm curious, I have a couple questions. I'm going to try so hard to keep it short. So I'm curious about your dynamic exposure control and how that relates to your signal to noise for different fluxes.
Mm-hmm.
And what the trade-off is. Like, I know you're using a delta doped detector and how I know that you're going to get really good quantum efficiency from that, but what your signal to noise looks like for different fluxes.
Yeah, so our goal, so because these flares are, as you saw, they go up by factors of 2, 4, 10 thousands, right? This is not high precision photometry. Like we don't need millimeg kind of photometry. So our goal is to have 10%. So signal to noise of 10 is what we want. And so if you decrease the signal to noise, but you have more flux, as long as we're maintaining roughly, and if you want the details, Tahina published this in a very nice paper, 2022. His last name is Rami Ramansoa, but if you look, which would be hard to spell, but you'll find it. You'll find it because the Sparks team is on there.
And
I am an author on it, so you can find it. But cool. He's the first author, and it was his work.
And then my other question is a little more broad, but as we as a field are kind of gearing up for what changes or what progress we want to make on our way to habitable worlds, where do you see Sparks fitting in amongst like past or existing missions like Cute and future missions like Mantis, and like what you hope to gain science-wise versus technology-wise on Sparks, and how all of that leads to Habitable Worlds Observatory?
Okay, that's a big question.
I know that's a big question.
I'll try and keep it short. I'll keep it really short. Scientifically, we're doing near UV and far UV simultaneously. So you get flare colors of rare, and we stare for like a month, right? Roughly. And so you get flare colors, flare temperatures, and some flare frequencies of these strongest ones. Technologically, and for Hab Worlds will observe M-star planets, but in transit, not in direct imaging. Technologically, we're demonstrating the delta dope detectors. So if everything goes as planned, then they are a contender for, there are other options, of course, but they could be a contender for the UV instruments. For for hub worlds, and then we've got these metal dielectric integrated filters that are already, just based on what's been tested in the lab, already baseline for UVEX. So that's our technology kind of contribution.
We are at time. We've got 2 more quick questions, but then everybody should just swamp her after.
Hi, excellent talk. Thank you so much for being here. I'm curious, as somebody who's working in like solar system science and space weather here from the sun, how much of like this research is fueled by like our results that we have from like say Mercury, Venus, and even Earth atmospheric loss, and like also like from Mars, Jupiter with the solar wind data that we have here? Like how much does that infer what we think about M or even G type stars outside of our solar system?
That's a good question. I have to be honest and say I came to to learn more about the solar system from the exoplanet world. So, so I was fueled by exoplanets and am now a devotee of solar system work, and am learning from you guys of all the things that you guys know, which is intimidating because you have so much data, right? And we're never going to have that much data, and I don't know. I have to reconcile those. But yeah, so I went the other way. I went from exoplanets to solar system. Mm-hmm.
So kind of related to that, and also to the question over here. You know, everybody wants to give you a reason to believe. I very much like that you're being agnostic. And just to give you an example, you know, so the photochemical lifetime of methane on Titan, anybody know what that is? It's like 100 million years, right? So Titan shouldn't have any methane, and yet it has nitrogen-rich in methane atmosphere. So I think that's a great kind of anecdotal piece of evidence for why you should continue to be agnostic. And then my question is maybe a bit too technical, so feel free to tell me to come to you afterwards. But I don't understand this has flare that you showed, this beautiful example with that you say has a period that is supposed to occur about once a day.
Yeah.
Why have we only seen one of those? I don't get that. Maybe I'm missing something.
Yeah.
But we've looked at.
No, I'll tell you why.